Assalamualaikum. My name is Ahmad Zulfahmi bin Muhammad Zulkifli. My matrix number is 22000099. Today I want to show you my video presentation on my experiments that I have done throughout this semester. Throughout this semester, I have done 5 experiments, which is firstly, M1 tension and kinetic friction. Second, DC1, which is measuring the internal resistance and the precision of a galvanometer. And SC2, determination of impedance of inductor and capacitor using an oscilloscope. Next, O2, refraction of light. And M2, rigidity modulus of wire by using Maxwell needle method. In experiment M1, the objectives are to study the kinetic friction and tension on a segment curve. Second is to study the relationship between the tension and angle of a segment curve. And third is to determine the coefficient of friction of the string. Next, I will give a small introduction on this experiment. A tension is the force transmitted through ropes, wires, or strings that is usually exerted when they are pulled by forces from each of their opposite ends. When a string attached to a curved segment is pulled in a uniform motion, the tension could be determined. However, the tension of the string depends on the different angles it is placed before motion. In this figure, the tension of the string is observed to be different in both positions M and N due to the friction delta F that exists on position M. Since the string is in constant motion, the total force that is acting on M is equal to the total force that acts on N. Thus, we will get this theory. And here is the methods that I used during this experiment. After doing the experiment, this is the results I obtained. From this experiment, the conclusion that I get is the experimental values of mu for the first condition is negative 6.03 plus minus 0.6 times 10 power of negative 3 and negative 3.28 plus minus 0.0001 times 10 power of negative 3 for the second condition. Second, the values of T0 when 0 degrees to when the range is 0 degrees to 360 degrees and the range 360 degrees to 720 degrees are 21.12 Newton and 1.86 Newton respectively. The difference in value is due to the number of circumference bounded by the wire string. The relative errors for each condition, which are 43.44% and 87.36%, are also different for the same reason. The third conclusion is the values obtained could be more accurate if the experiment is operated precisely with the uniform velocity each time and not interrupted by the air around the laboratory. In experiment DC1, I conduct 4 different parts of this experiment with different objectives too. DC1A is to determine the internal resistance measurement in a galvanometer. DC1B is to determine the sensitivity of a galvanometer, and DC1C is to determine the resistance R when a voltmeter is connected in parallel with both the ammeter and the resistor. DC1D is to determine the resistance R when a voltmeter is connected in parallel with the resistor but in series with the ammeter. So, I will give a brief introduction on every parts of this experiment. In DC1A, the The introduction that I will give is any conductor, no matter how good its performance, must has resistance. In a galvanometer, there is a resistance known as internal resistance, which is brought into by the resistance of a wire coil used in a circuit. Based on the circuit constructed in this figure, the internal resistance of the galvanometer can be determined, and the lower half of the resistors R1 and R2 are connected to the galvanometer, which is also connected in parallel to the potentials V1 and V2. This circuit is also known as the potential divider, which divides the voltage V to V1 and V2. Thus, the relation obtained is as follows. Hence, we get those theories. Next, DC1B. Here, we determine the galvanometer sensitivity. The definition of the sensitivity of a galvanometer is the current needed in order to deflect the pointer needle of the galvanometer to 1 unit of its scale. Given that a current Ig flows through the galvanometer and causes a deflection, this theory is given. In experiment DC1C, I determine the resistance in the voltmeter when it is connected in parallel with resistor and emitter. The measured readings of a voltmeter and an emitter in a circuit are not the real readings. This is because a small current will always flow inside these two instruments through the coil. However, when the readings from both of the voltmeter and the emitter is recorded, the actual reading can be determined. In a circuit, there are two different methods to connect these instruments in order to measure the resistance, which is either in parallel or in series. From the circuit constructed in this figure, the apparent voltage is said to be the value of voltage across the emitter and the resistor. Thus, we use these theories. In this C1D, we determine the resistance in the voltmeter, which is connected in parallel to resistor only. So, in this figure, shows a circuit where the voltmeter is exclusively connected to the resistor only. The value of actual current through R is I minus IV, which is totally different from experiment DC1C. From the equation mentioned, I is the current obtained from the emitter, while IV is the current that flows through the voltmeter. Hence, we use these theories. And here is the methods that I used during this experiment. And here is the results that I got from every part of this experiment. Hence, the conclusions that I get from each part of this experiment is, in DC1A, the internal resistance measurement of the galvanometer stands at 1103 plus minus 28 ohm. In DC1 and in DC1B, the sensitivity of the galvanometer is 6.14 times 10 power of 6 a d power of negative 1. In DC1C, utilizing method 1 proved to be the most precise approach for calculating resistance when a voltmeter is connected in parallel with both the emitter and the resistor. And in DC1D, method 1 remains the most accurate method for resistance calculation when a voltmeter is connected in parallel with the resistor but in series with the emitter. These experiments are deemed successful as all findings fall within the acceptable range of values. In experiment SC2, the objective is to determine the voltage measure across a pair of resistor inductor and a pair of resistor capacitor circuits in series, and to measure the impedance of an inductor and a capacitor. For the introduction, impedance is known as the combination of resistance as well as both inductive and capacitive reactance. Reactance is a property that opposes a change in current and is found in both inductors and capacitors. Since it only affects changing current, reactance exists only alongside AC power and depends on the frequency of the current. The equations for both of these reactance are as follows. This property is a complex number which contains both real and imaginary parts. The real part of impedance is resistance, while the imaginary part is reactance. Impedance has both magnitude and phase. The equation below sums up the meaning of impedance, where R represents the resistance, is SL is the inductive reactance, and SC is the capacitive reactance. Meanwhile, for the real parts of impedance, the relationship between each one of the voltage involved can be summed up in a vector diagram as follows. And here is the methods that I used during this experiment. Here is the results obtained from the experiment. From the results obtained, I conclude that the impedance obtained for the resistor inductor circuit and the resistor capacitor circuit are 7.94 ohm and 7155.39 ohm respectively. And the theory VRL is equal to VR plus VL is not accepted because the value of total voltage across the resistor and the inductor is not measured algebraically, but rather the sum of vector between them. Thus, trigonometry and Pythagoras theorem are applied instead. And third, from the experiment conducted, the experimental values for the capacitance and inductance are precise when compared to the theoretical values with error percentages less than 5% for both. However, the error percentage obtained when comparing the actual and experimental values of RL and RC are really big and considered unacceptable. In experiment O2, the objective are to obtain the refraction and dispersion of light through prism and to study the behavior of light through prism of different medium density, and third is to determine the angle of light's refraction through prism. The direction of the light path changes when it moves from one medium to another where the speed is different. Light is bent towards the normal and vice versa when it moves from a medium with a high refractive index, higher speed, to one with a low refractive index, which is lower speed. Snell's law describes the relationship between the speed v1 in the first medium with refractive index n1 and the speed v2 in the second medium with refractive index n2, where I is the incidence angle and R is the refraction angle. When a light beam strikes one of a prism surface, both the first and second surfaces bend the beam. The emergent ray deviates from the incoming ray from a parallel path, and the amount of the deviation is determined by the index of refraction, the refracting angle apex of the prism, and the angle of incidence at the initial surface. When a ray enters a prism from a direction perpendicular to the bisector of the prism's refracting angle, the angle of deviation is at its minimum. The angle of minimum deviation is what this is known as. Parallel light from a slit is split into different colors when it travels through a prism, depending on their wavelengths. Different colors depart from the slit through different angles. A telescope that is aimed to receive parallel light can be used to observe discolored slit images. The prism spectrometer works on the same arrangement as seen in this figure. And here is the methods that I used during this experiment. The results for O2 is given as follows. In this experiment, I can obtain that the experimental value of the dispersion is equal to negative 3717.73 plus minus 34.04 cm power of negative 1 with the relative uncertainty of 0.92%, while for the dispersive power is equal to 0.0370 plus minus 0.0003 watt with the relative uncertainty of 0.81%. In experiment M2, the objective is to determine the modulus of rigidity of given wire by dynamical method using the Maxwell needle. The rigidity modulus or shear modulus can be defined as a quantity that represents the coefficient of shape elasticity of a material. It shows the resistance of the material to endure the shear force which can result to lateral deformation of the material. Thus, this property is a fundamental based in science, material, and engineering to study the range of deformation that a certain material can withstand under shear force exertion upon the area of the material. Thus, the relation of shear stress to shear strain is another uncomplicated definition of the rigidity modulus. Each kind of material owns different value of rigidity modulus, as this property depends on the elasticity of the material and the amount of force it can handle. As conclusion, the more rigidity modulus of the material, the more it will be difficult to bend and vice versa. Maxwell needle consists of a pair of solid brass cylinder and a pair of hollow brass cylinder. All of them are equal in length, and during experiment, they were inserted in a long hollow root cylinder. In this experiment, a wire was vertically attached at the end of retort stand, while the other end is connected in the Maxwell needle, leaving it to be hanging at mid-air. And the theory is as follows. And here is the methods that I used during this experiment. The results obtained from this experiment is as follows. To wrap up, the rigidity modulus of the wire by applying the Maxwell needle method is determined to be 0.000000567 plus minus 26.9 E Pascal. Lastly, thank you for listening to my explanation throughout this video. Bye.